In this video, we're going to talk about number systems. The first number system that you need to be familiar with is the decimal system. Now, when you hear the word decimal, what do you think of? Think of the prefix deci. What does that mean? When I hear the word deci, I think of 1/10 of a whole. For example, there's 10 decimeters in 1 meter. I also think of the word decade. A decade corresponds to 10 years. And so deci is associated with 10. And in fact, the decimal number system is a base 10 system. And so what this means is that there's 10 different numbers in the decimal system. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's a total of 10 numbers. Now, this system is used for everyday counting. For example, 12 or 36 or 468. We use the decimal system to represent numbers, and it works pretty well. Now, the next system that you need to be familiar with is the binary system. So when you hear the prefix bi, what do you think of? Bi means 2, and so the binary system is a base 2 system. It's very useful for computers or any type of digital circuits. There's only 2 numbers here, 0 and 1. In a typical digital computer, 0 means off, 1 means that the system is in the on state. Next, we have the octal system. And when you hear the word octal or octa, what do you think of? I think of an octagon. An octagon is basically a polygon with 8 sides. So octa means 8. So the octal number system is a base 8 system. So there's 8 numbers that we can use in this system. The first being 0, and then 1, 2, 3, 4, 5, 6, 7. So that's a total of 8 numbers, including 0. Next, we have the hexadecimal system. Now, what is meant by the prefix hexa? Hexa, think of a hexagon. A hexagon has 6 sides, and so hexa means 6. We know decimal corresponds to 10, and so 6 plus 10 will give us 16. Therefore, the hexadecimal system is a base 16 system. And so the numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have all 10 numbers in the decimal system, but we also have 6 letters. And so those letters are A, B, C, D, E, and F. Now A corresponds to 10 in the decimal system. B in the hexadecimal system corresponds to 11 in the decimal system. C is 12, D is 13, E is 14, F is 15. So that's a total of 16 numbers, including 0. Now let's talk about how we can convert a decimal number to a binary number and into an octal and a hexadecimal number using the technique called successive division. So let's say we have the number 348. If you see a subscript 10, that means it's in the base 10 system, which means it's a decimal number. So the first thing you want to do is take 348 and divide it by 2. So if you type that in, you'll get exactly 174. So it's 174, remainder is 0. Next, take 174 and then divide that by 2. So that's exactly 87. So it's 87, remainder 0. Next, if we take 87 and divide it by 2, we're going to get 43.5. So it's 43, remainder 1. But first, let's write it like this. So this 43 gets transferred here, and then to get the remainder 1, you multiply 2 by 0.5, and that will give you the remainder 1. I'm going to write my answer like this for now. Now, if we take 43 and divide that by 2, that's going to be 21.5, which is 21, remainder 1. And then we need to take 21, divide that by 2. So that's 10.5, which is 10, remainder 1. And then 10 divided by 2 is exactly 5, so 5 remainder 0. And then 5 divided by 2 is 2.5, so 2 remainder 1. And then 2 divided by 2 is exactly 1, so 1 remainder 0. And then 1 divided by, I'm running out of space here, 1 divided by 2, that's 0.5, so 0 remainder 1. What we have on top is the least significant bit, and this here is the most significant bit. Now you can find your answer just by looking at all of the remainder values, which is here. And so that's the binary number that's equivalent to 348. So you need to read it from the bottom to the top. So the answer is 1, 0, 1, 0, and then 1, 1, 1, 0, 0. So that's how we can convert a decimal number into a binary number using successive division. Now let's convert this number into an octal number in the base 8 system. So if we look at the last example, where we converted 348 into a binary number, we were dividing it by 2, because binary, it's based on the base 2 system. Bi means 2. The octal system is based on the base 8 system, so instead of dividing it by 2 and collecting the remainders, we're going to divide it by 8 this time. So 348 divided by 8, that's going to be 43.5. So this is 43 remainder. Now to find the remainder, multiply 8 by 0.5. So 8 times 0.5 is 4. So it's 43 remainder 4. Next, take 43 and divide it by 8. And this will give you 5.375. So it's 5 remainder, and then multiply the 8 by 0.375. 8 times 0.375, that will give you 3. Next, take the 5 and divide it by 8. Now, 5 is less than 8, so we can say that 8 goes into 5 0 times with a remainder of 5. But if you do 5 divided by 8, you're going to get 0.625. And so the 0 gets transferred here. And then if you multiply 8 by 0.625, you should get this number, the original number that you started with, which will go here. So this is the most significant digit, and above we have the least significant digit. So we're going to read it from the bottom to the top. So 348 base 10 as a decimal number is equivalent to 534 or 534 in the octal system. And so that's how you can convert a decimal number into an octal number using successive division. Now let's talk about how to convert the decimal number into a hexadecimal number using successive division. So let's use the same number, 348. Let's convert it to a hexadecimal number. Now the hexadecimal number is basically a number in the base 16 system. So this time, instead of dividing by 2 or 8, we're going to divide by 16. So if we take 348 and divide it by 16, this will give us 21.75. And so that's 21 remainder. To find the remainder, multiply 16 by 0.75. So 16 times 0.75, that's 12. So it's 21 remainder 12. Now let's take 21 and then let's divide that by 16. So 21 divided by 16 is 1.3125. And so we have 1 remainder Now let's multiply 16 by 0.3125. And that's going to give us 5. So it's 1 remainder 5. Next, take 1 divided by 16. Now we know 1 doesn't go into 16. So 16 goes into 1 0 times with a remainder of whatever you see here. In this case, a remainder of 1. And so we're going to read it this way. So we have a 1, a 5, and a 12. Now 12, because it's larger than 9, we need to convert it to a letter. So remember, 10 corresponds to A, 11 corresponds to B, and 12 corresponds to C. So it's 1, 5, C. So therefore, we could say this. 348 in the base 10 system is 15C in the base 16 system. And so that's how we can convert a decimal number into a hexadecimal number using successive division. Now, for those of you who are looking for a specific conversion technique, such as how to convert from octal to hexadecimal, I'm going to post some links in the description section of this video. So feel free to take a look at that, and you can find more specific conversion techniques. But just to review, we talked about converting a decimal number into the binary, the octal, and the hexadecimal system. And we use division to accomplish that. Basically, or more specifically, successive division. Now, what if we want to go backwards? Well, the opposite of division is multiplication. So we need to use some sort of multiplication process to go back into the decimal system. And I want to show you the pattern of going from binary to decimal, hexadecimal to decimal, and octal to decimal. So let's start with this binary number that we calculated earlier in this video. And so what we're going to do is we're going to multiply these binary numbers by powers of 2 because the binary number is in the base 2 system. So the first one, we're going to multiply by 2 to the 0, and the second one by 2 to the first power. And then the pattern will just continue. So as you go to the left, you could see that the exponents are increasing by 1. And so we're going to have 1 times 2 to the 8, and then we're going to multiply these two. So that's going to be 0 times 2 to the 7, and then 1 times 2 to the 6, and then 0 times 2 to the 5th, and then after that it's 1 times 2 to the 4th, plus 1 times 2 to the 3rd, plus 1 times 2 squared, plus 0 times 2 to the 1st, plus 0 times 2 to the 0. Now, I don't need to write all of this because we really don't need the zeros, but I want to show you the process by which we can convert all of these other number systems into the decimal system. So 0 times anything is 0, so these numbers we can ignore. 2 to the 8th power. If you multiply 8 2's together, so if you multiply 2 by itself 8 times, that's going to give you 256. 2 to the 6th power is 64. 2 to the 4th is 16. 2 to the 3rd is 8. 2 squared is 4. And so 256 plus 64 plus 16 plus 8 plus 4, that will give us our original number of 348 in the base 10 system. And so that's one way in which you can convert a binary number into a decimal number. Now let's talk about how we can convert an octal number into a decimal number using multiplication. So the first number that we see, we're going to multiply it by a power of 8 rather than a power of 2 in the case of binary numbers. But the pattern is going to be the same. So instead of 2 to the 0, we're going to multiply the first one by 8 to the 0, and then the second one by 8 to the first, and the third one by 8 squared. So it's going to be 5 times 8 squared plus 3 times 8 to the first power plus 4 times 8 to the 0 power. Now 8 squared, that's basically 8 times 8, which is 64. And then 5 times 64 is 320. Now 3 times 8 is 24, and anything raised to the 0 power is 1. So 8 to the 0 is 1. 1 times 4 is 4. So we need to add 320 plus 24 plus 4, and that will give us 348 in the base 10 system. And so that's how you can go back from the octal system into the base 10 system. Now let's talk about how we can convert a hexadecimal number into a decimal number. Now the first thing we're going to do is change C. Recall that A corresponds to 10, B corresponds to 11, and C corresponds to 12. So the first number we're going to multiply by a power of 16. So the first one is going to be 16 to the 0, and the second number we're going to multiply by 16 to the first, and the last one by 16 squared. So it's 1 times 16 squared plus 5 times 16 to the first power plus 12 times 16 to the 0 power. 16 squared is 256. 5 times 16 is 80. 16 to the 0 power is 1, so we have 12 times 1, which is 12. And adding these three numbers will give us 348. So notice that if you want to go from the binary system to the decimal system, multiply everything by powers of 2. If you want to go from, let's say, the octal system to the decimal system, you need to multiply by powers of 8, because the octal system is a base 8 system. And for the hexadecimal system, which is in the base 16 system, multiply the numbers by powers of 16. And any letters, you need to convert it into a number. Now, this pattern of power multiplication is also found within the decimal system as well. So the first number we're going to multiply by 10 to the 0, the second one by 10 to the 1, and the third by 10 squared, because this number is in the base 10 system, as we could see by the subscript there. Now 10 to the 0, we know it's 1. 10 to the 1 is 10. 10 squared is 100. So we can see that the 8 is in the 1's place, the 4 is in the 10's place, and the 100, or 10 squared, that's in the 100's place, which makes sense for a base 10 system. So we can represent 348 as being 3 times 10 squared plus 4 times 10 to the first power plus 8 times 10 to the 0 power. Now 3 times 10 squared. We know 10 squared, or 10 times 10 is 100. 100 times 3 is 300. And here we have 4 times 10, which is 40. 10 to the 0 is 1, so 8 times 1 is 8. So 300 plus 40 plus 8 is 348. And so this process, this multiplication by the powers, this is a base 10 system, so we multiply it by powers of 10. We can also use it for the decimal system, or any number system for that matter. Now there's another way in which we can convert 348 into a binary number, and let's talk about it. Now it's helpful to understand the pattern for binary numbers. We know the first number will be multiplied by 2 to the 0, and then the next one by 2 to the first, and so forth. Now 2 to the 8 is 256, and 2 to the 9 is 256 times 2, so that's going to be 512. And so I'm going to write these numbers down. So we have 512 as 2 to the 9, 256 is next, that's 2 to the 8, and then 128 for 2 to the 7, and 64, 32, 16, 8, 4, 2, and 1. So we're going to use the subtraction method to convert this into a binary number. The highest number that can be broken down into a base 2 number, which are these numbers here, the highest number that's less than 348 is 256. Now, if you subtract 348 by 256, this will give you 92. Now the highest number that is less than 92 at this point is 64. Now, if we do 92 minus 64, that's going to give us 28. The highest number under 28 is 16. So now let's subtract 28 by 16. That will give us 12. So we can use an 8. 12 minus 8 is 4. And then we'll stop at 4. So notice that if you add 256 plus 64 plus 16 plus 8 plus 4, it will give you 348. Now let me bring your attention back to the bottom. So every number that we use, every number that is highlighted in red, replace it with a 1. Every other number that we didn't use, replace it with a 0. And so that's another way in which you can convert a decimal number into a binary number. Now, any zeros to the far left are insignificant, so we don't need this 0. So our answer starts from here. And this is the binary number that we had in the beginning. 1010111100. And so that's another way in which you can convert a decimal number into a binary number using subtraction. Now, once you have this binary number, you can easily convert it into an octal number or into a hexadecimal number. And the way you do this is you group it. 2 to the third power is 8. And so if you want to go from the binary system, that is a base 2 system, into an octal system, that is a base 8 system, you need to group the binary numbers in groups of, guess what? 3, the exponent that you see here. And so let's separate it into groups of 3. Now the first group is 1, 0, 1. The second group is 0, 1, 1. And the third group is 1, 0, 0. So now each group of 3 binary numbers, convert it into a decimal number. And remember, to convert binary to a decimal, we need to multiply by powers of 2. So we would multiply this by 2 to the 0, which is 1, this one by 2 to the 1, which is 2, and this one by 2 squared, which is 4. So this is 4, 2, 1. So at this point, it's easier to use 4, 2, 1 instead of powers of 2. But understand that it's based on powers of 2. Now we have a 1 with a 4 and a 1 with the 1. So 4 plus 1 corresponds to 5. 0 plus 2 is 0, so we could ignore any zeros. Now let's do the same thing for the others. 4, 2, 1. So here we have a 1 associated with the 2 and the 1. 2 plus 1 is 3. And for the last one, we only have a 1 associated with the 4. And so that becomes 4. And now we can see our answer. So therefore, this binary number is equivalent to 534 in the octal system. And we had that number earlier in this video if you want to rewind it. And so that's how you can convert a binary number into an octal number by grouping the binary numbers in groups of 3. Now let's see if we can apply the same conversion process when converting a binary number into a hexadecimal number. So let's use the same binary number that we've been using in this video. Now 2 to the 4th power is 16. So 2 corresponds to a number in the binary system. 16 corresponds to the hexadecimal system. So to convert from binary to hexadecimal system, we need to group the binary numbers in groups of 4, since 2 to the 4 is 16. And so here we're going to have the first group of 4, and here is the second. Now notice that we don't have a group of 4 on the left. In that case, just add 3 zeros. So we have 0, 0, 1 for the left side, and then in the middle, 0, 1, 0, and then on the right side, 1, 1, 0, 0. Now we're going to convert these binary numbers into decimal numbers. So we need to multiply by powers of 2. So this is going to be 2 to the 0, 2 to the 1, 2 squared, 2 to the third. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. So this time, instead of writing powers of 2, we're going to use 8, 4, 2, and 1. Now for the left side, we have a 1 associated with the 1. So the binary number 0001 has a decimal value of 1. In the middle, we have a 1 next to the 4 and a 1. So 4 plus 1 will give us 5. For the right side, we have a 1 next to the 8 and the 4. Now 8 plus 4 is 12. But when dealing with hexadecimal numbers, you need to convert it into a letter. A is 10, B is 11, C is 12. So it's 1, 5, C. So our answer is 15C in the hexadecimal system, which we had earlier in this video. And so this process of grouping binary numbers can be useful, let's say, if you want to convert from the octal system to a hexadecimal system. So you would convert the octal system to a binary system, and from binary, you would go to the hexadecimal system. Now, if you want to see some examples of this process in action, on YouTube, you could do a search, octal to hexadecimal conversion, and then type in organic chemistry tutor. And then you could find a video that I made on how to convert from octal to hexadecimal and how to convert from a hexadecimal system to an octal system. But now there's one last thing I want to talk about, and that is how to convert a decimal number into a binary coded decimal number. Now, for the binary coded decimal system, what happens is each digit you represent it as a group of 4 binary numbers. So 3, 4, 8, we're going to convert each number separately into a binary number using groups of 4. So since we're using a group of 4 binary numbers, it's best to write this 8421. Now, to get 3, we need to add up 2 and 1. And so every number that's highlighted, replace it with a 1. The numbers that we don't use, replace it with a 0. So the binary number 011 correlates to 3. Now, to get 4, we only need to use 4. So we only need to replace that with a 1. Everything else, replace it with a 0. So 0100 correlates to 4. Now for the last one, we only need to use an 8. So we're just going to replace that with a 1. So 1000 correlates to 8. So 348 is equivalent to the binary coded decimal 0011 0100 1000. And so that's how you can convert a decimal number into a binary coded decimal. Now let's say if we want to go backwards. Let's say if we have the number 11 1001 0101. How can we convert this into a decimal? Now keep in mind, this is not a regular binary number, but it's a binary coded decimal, which means we need to break it up into groups of 4. Here we only have 2 numbers, so we need to add 2 zeros. So the first group of 4 is going to be 0011, that's for this side, and the second group of 4 is 1001, that's for the middle, and on the right side 0101. So let's write the numbers 8421 under each group of 4 binary numbers. Now on the left, we have a 1 associated with a 2 and a 1. So 2 plus 1 is 3. In the middle, we have a 1 associated with the 8 and a 1. 8 plus 1 is 9. And on the far right, we have a 1 next to the 4 and a 1. 4 plus 1 is 5. So this binary coded decimal is equivalent to 395 in the decimal system. So that's how we can go from BCD to decimal. And so that's it for this video. Hopefully it gave you a good introduction into number systems and how to convert from one number system into another. Thanks for watching.